Okay, let's get moving here. This is video number 47, where the object is to answer the questions raised in video number 46 from yesterday in our enrichment week. So here we are one more time, explaining how we put together equilateral triangle inscribed in a circle with radius 1. Although, like I said before, the radius really doesn't matter. If I know 1, then I just multiply by any old scale factor, and I know whatever radius I want, depending on the scale factor, okay? So here we go. There was the center that allowed me to create the circle, and there's the only data that I have, okay? The spokes, as I mentioned them before, each with 1, and I'm going to extract, I'll use that word, and the triangle that I extract, if I know 1, I just multiply by 3, we agreed to that, and if I look carefully at it, this is 1 and this is 1. When I drop my perpendicular bisector, I find that the game is up. We've reached a place where we can't continue anymore. We have to move on in our mathematical skills. Fortunately, with the theorem of Pythagoras, I have to know 2 sides. If I only know 1, I have no hope of getting the correct answer. So I have no idea what the length of this guy is, and I have no idea what half of it is, and if I can't find that, how am I supposed to find the height or the altitude? So we need new mathematical tools to continue here, and I intend to teach you those tools, not today. I just brought that up yesterday to show you that with the tools that we have so far, we're unable to solve a problem like this. All right, so that answers why I can't do a simple problem, easy, simple problem, like inscribing, using circle math, a equilateral triangle inside a circle of radius 1. So we'll move on from that, and we'll certainly talk about it later, and certainly we'll eventually solve this problem using new tools that I mentioned to you in class previously and that we'll go on to later. So now I agreed that we're going to use radicals now to solve more complicated problems, and I need to find the area of this pentagon. Again, we use the proper word. It's an irregular pentagon. Why? It doesn't inscribe in a circle. So before, back in the day when we were in class together, we were unable to do anything unless it was a triple. And now, you don't have to be a triple anymore. You could be all sorts of different types of pentagons, and we can solve them easily. By the way, before I forget, if I inscribe a pentagon in a circle, I'm going to run into the same exact problem. I won't be able to solve using the theorem of Pythagoras and radicals because I'll only get one side. If you want to experiment with that, you can do it yourself, but you'll see that what I'm telling you is true. So now we attack this problem here, and it's a compound, two-dimensional shape. You should know the meaning of compound now. And what I've done, like I mentioned yesterday, is I just plopped an equilateral triangle right on top of a trapezoid. And of course, I'm going to try to make the numbers work. And I'm going to save myself some trouble now. And hopefully those of you who don't understand me will send me a letter. But when I drop the perpendicular bisector, there's no need, as I've said a number of times, to go through the whole rigmarole of a squared plus b squared equals c squared, because if the equilateral triangle is 1, 1, 1, and then the equilateral triangle is 3, 3, 3, well, it's just a scale factor of 3 to 1. So if this equaled, as we already know, 3 over radical 4, okay? The area of this one must equal 3 radical 3 over 4. That is the scale factor times this. there's another example of how similarity is a powerful tool that enables you to work without doing all this math. Now, you could do this, and you get 3 over 2 over here, but when you do the work, you will see that you're going to get radical 27 over 2, and you'll multiply that by 1/2 using the area of a triangle. And since this can be simplified as previously explained, 9 times radical 3 divided by 4, then you see exactly how I came up with this answer, if you've been paying attention to me. And I see that you can see through the glare there. I know I can, so hopefully that makes sense. Send me an email if you don't. All right? So, there we go. We're in a situation now. We've explained how we came up with the area of the equilateral triangle. It's 3 radical 3 divided by 4. And now we have to add the trapezoid. So I'll do that down here. Well, if you recall, I need somehow to find the height of the trapezoid. But I've been given the height of the whole figure here. So it's 5 over 2 radical 3, which is data, which of course is friendly data, to make the numbers easier and more comprehensible to 8th graders. And now it's minus whatever we got before, which was 3 radical, 3 radical 3 over 2, which was the height of this. And the height was going to work out to 3 radical 3 over 2, because again, it's just a scale factor and everything works out the same exact way. So now, when I subtract the whole length from the partial length of the trapezoid from the whole length, and then I end up getting 2 radical 2 over 2 radical 3. And the 2's cancel, so the height of this trapezoid is radical 3. Again, send me an email, make me explain it again if you don't see what's happening, or you can slow down the video and go over it again. But here's the whole height, here's the height of the equilateral triangle. It's been explained to you. There's the area, and now I'm trying to figure out, given the height now, and given both bases, I fill in the formula, which you're supposed to know, and again, the h is radical 3, and so it turns out to be the height, radical 3, times the sum of the bases, which is 3 plus 2, divided by 2. And you're supposed to know the formula for a trapezoid. You'll look it up, that's how I got it. And that becomes radical, let's just do it right side up, 5 over 2 radical 3. Okay, 3 plus 2 is 5. There's the 2, there's the radical 3. Oh, I remember from 6th grade that I can't add the fractions unless the denominator is the same. So I rewrite, and I have 3 radical 3 divided by 4 plus 10 over 4. I just doubled everything. 5 over 2 is equivalent to 10 over 4, as you well know. And there I am, and now I can add them together, and the area of this particular pentagon is 13 radical 3. Are we good still? Yeah. 13 radical 3 divided by 4. There's the correct answer. I'm going to give you another one so that you can practice. The problem's just the same. I'll just change the numbers. And now I was asked to find the perimeter. So let me erase all this stuff here. A lot of clutter here. I'm going to keep my same guy there. The answer's circled over here so you know what I came up with. And now I need to find the perimeter. And so that means I got to find this guy right here. The figure is symmetric. I need to find the slants here. So let me erase all the superfluous stuff. okay? And I still divided this since it's a compound figure. And now I draw a new altitude to create a right triangle here. After all we know is the theorem of Pythagoras and radicals so far, so that's all I know how to do. If I know this guy, obviously I know the other side. So I'll just figure out one side, and I should be in great shape. Well, if this is 3 and this is 2, and there's perfect symmetry in the figure, as you can see, then 1/2 plus 2 plus 1/2 equals 3. We have the number down correctly. So I have two sides, and all I have to do is figure out, because this side over here is radical 3. We already figured out the height. So here we go. A squared plus b squared equals c squared. And now I want the hypotenuse. So it's radical 3 squared plus 1/2 squared must equal the hypotenuse squared, which is the slanted side of the pentagon. And here we go. Well, radical 3 times itself, of course, is 3. You're supposed to know that. We taught you that a long time ago. 1/2 plus 1/2 is 1/4. And that equals h squared. We're calling this h since we're regarding it as a hypotenuse. Well, again, I rewrite, and if I multiply both sides by 4, I get 12 over 4 plus 1 over 4. You remember 6th grade, I presume. And that equals 13 over 4. And then I need to take the square root, put the hat on it, as we say, and I get radical 13 over 2. Well, I'm almost done. If this is radical 13 over 2, then this must be the same thing. Radical 13 over 2. Well, what's radical 13 over 2 plus radical 13 over 2? I refer you again to 6th grade. Radical 13 over 2 is 2 radical 13 over 2. Okay? So both sides of this, as this cancels, are radical 13. So 3, that's this side, plus 3, that's this side, plus 2, that's the bottom side of the trapezoid, plus radical 13. And when we put everything together, we get a number, very common in math, 8 plus radical 13. Well. We explained to you already that you can't put these guys together. They're not like terms. So if you really need for engineering purposes or you're a scientist, then you simply use your calculator and round to whatever you need to round to. In math, we regard this as the answer for perimeter. And this is the answer for area. Okay, I'll shut this off now, and in the next video, I'll propose some more problems. I don't want to rush along on this. It's just giving you an idea of challenging problems, what you can do with radicals and the theorem of Pythagoras. Okay.